Welcome, Mr. Mihir Khatri. Let me give you some introduction about sir. He is our alumni of 2018 batch. Currently, he is a production and maintenance engineer in Bharti Enterprise. He is working there for 2 years. Bharti Enterprise is basically working as a traders and manufacturers of industrial transformer accessories like oil gauge, OTP, oil stop valve, radiator valve, etc. In our university, many IoT subjects are being offered like IoT, Arduino, PLC, and microcontroller. So in this session, we will get to get many knowledge about this thing. So now I would like to request Mihir sir to please share your valuable knowledge to us, sir.
Thank you, sir. First of all, I would like to thank Vinay sir, Jiten sir, Chirag sir, our electrical department for giving me the opportunity to present this webinar. I would also like to thank Parallel University. Uh, PU has always aided our dreams, and I hope so it keeps doing it. And moving on to the webinar. So today's webinar has been aimed to give you a thorough idea about the embedded systems and its role in electronics. So let's begin. So here's the overview. We will come to know about what are the embedded systems, parts of an embedded systems, the power supply, which are the constituent parts of the power supply, controller, IDE, sensors, actuators or display and communication. So we'll discuss each of them in detail in the coming slides. So what are embedded systems? An embedded system is a controller-based hardware system with software that is designed to perform a dedicated function. Here, the controller, which is referred to, might be a microcontroller for the low-end applications and a microprocessor for the high-end applications. So it depends on application to application which type of controllers are used. But in short, the main thing is that a controller is them coordinating all of the other parts. So here is written that at a core is an integrated circuit designed to carry out computation for real-time operations. It's a real-time operating system. So what embedded system generally does is that it takes inputs from the environment with the help of sensors. The sensors pass it on in the form of electrical signals to the controller or the software. The controller processes it and does some useful work out of it and outputs the signals to the control to display. It might display something, a value or something, a result or something, or it may actuate something like relays or anything in the form of a control systems. So this is what a general embedded system looks like. Okay, and embedded systems are available everywhere. You might see like AC, washing machine, your oven. They all are a part of embedded systems. There are different levels of it. Like if you go to a low level, the calculator is an embedded system. There's a low level embedded system calculator, then a digital timer, a multimeter you use. They are all the low level embedded systems where a simple controller is used which does all of the tasks. Coming to the medium level, you might see washing machines, ACs, then oven. PLC is also a medium level controller embedded system. Okay, they use somewhat a high level of controllers to do more amount of tasks. The number of pins are high. Okay, and going to the extreme level, high end, we use processors, not controllers, and we may also use DSPs, the digital signal processors for it, and they include the mobile, the computer screen, laptops. Okay, all of them are the high-end embedded systems. So embedded systems are present everywhere you see, and they form a very integral part of electronics. Okay, and the embedded system can perform as an independent system or as a part of a large system. Okay, so the calculator, it performs as an independent system. It is not dependent on anything. It uses the input from the user and calculates it and displays it in the LCD. But talking about a computer, it's actually a combination of 3 to 4 embedded systems, different embedded systems. It is combined together. So embedded systems can perform on their own or as a part of a group. Okay, so how would you distinguish any electronics from an embedded system? So the first thing is that embedded system uses a controller. You may say that the fan regulator is an electronic product, but it's not a embedded system, because all you do is change the potentiometer value, and in turn that value is controlled. The value controls the amount of voltage you are giving to the fan. So it's not a controller. So there is no any controller in between which is given to them. Only the pulses are controlled. So that's not a controller system, embedded system. The embedded system uses a controller for each and every process you do. Okay, so that's an embedded system. So now there are different parts of embedded system. The first one is the power supply, which each and every system has. It's very basic. Then there is a controller, the brain of the embedded system. Then there is IDE, or the integrated development environment. It's a software through which the controller, the brain of the embedded system, is coded. Okay. Then there are sensors. These are the senses of an embedded system. It is this through which the controller reacts to the environment. Okay, it senses, it receives the input from the environment. Then there are actuators or displays. And at last, there is communication. So now we'll discuss each of them, this in detail. So the first thing is power supply. So generally, it is called as switched mode power supply, or SMPS. You may also call it as UPS, universal power supply. In industry, the general term which is used for the general terminology which is used for power supplies is for 85 to 265 volt AC or DC. You can give both AC as well as DC to the power supply, and it works on both 50 to 60 hertz. This kind of power supply is different from the bulk transformers as we use. We generally used to use in old days, but this is what conventionally used today. It uses a very high switching frequency. It has about 100 to 132 kilohertz. So at the core, there is an IC which mainly controls the pulses. Okay, the pulses are given to the transistor, which switches the voltage, and which switches in PWM and controls the voltage given to the primary of the transformer. And at the secondary, the voltage is received accordingly as per the transformer induction rule. Okay, so these types of transformers are many types. Okay, the mainly types are more known types are DC converter, flyback converter, a forward converter, and a self-oscillating flyback converter. In industry, this DC-DC converter is also of two types: buck converter or boost converter. And in industry, DC-DC converter and flyback converter, these two are used in large quantities. Okay, they are used mainly. Now, the advantages of this type of control, this type of SMPS, is that it is very small in size as compared to the bulk transformer supplies we used earlier. Okay, and it is very efficient than the conventional bulk transformer power supply. So at the center of this power supply, there is a switching IC and an SMPS transformer, which we call it. It is also called as the ferrite transformer, or the SMPS transformer, or the pulse transformer. It uses a ferrite core, and it works on very high frequency. The normal bulk transformer uses 50 hertz sinusoidal wave as in its primary, 50 hertz operating frequency, whereas this operates in the range of 100 to 132 kilohertz. So it operates on much higher frequency and is much small in size. But due to this such high working frequency, it also induces many harmonics in the means. So it is very important to use a pi filter at both the input and output of this SMPS to cover out the noise suppression. And the main advantage of this is that even if at output there is some short circuit or anything, it handles them very well, because the IC which is used for switching sees it senses the amount of current, which it senses it, and it stops switching, and at that moment the output is stopped. Okay, now, and once the short circuit is cleared, the output is regained again. So this is how it in general works. This is the most basic form of an SMPS, the most basic form. Here is the AC main input is applied. Before this, there is also a fuse applied for overcurrent protection. An MOV is used for over voltage protection, and the pipe filter is also employed for the noise suppression. And a pure sinusoidal AC is presented between these 2 points. So that comes here and it gets converted to DC as a bridge rectifier. So across this bulk capacitor, a DC is uh, regained. Almost it is of 400-volt DC. It's a very high voltage. So that DC is applied to this IC. Uh, so for here, this is the SMPS transformer or the pulse transformer, you say, and this is the primary of the ferrite transformer. Okay, and the primary is connected with a switch. There is a MOSFET. There is an IC in which the MOSFET is embedded, and it is connected to ground. Okay, so this IC, the IC, it is mainly there are many ICs available, but most of the favorite is the TOP switch. This IC has many configurations ranging from 221 to 224, and the specialty of this IC is that it is embedded everything. There is a MOSFET embedded in it. There is a current sense embedded in it, a power supply, everything it is in this. So you don't need to connect any external thing. The crystal oscillator and everything is in it. Okay, it uses an RC oscillator. So how it functions is that the voltage DC is applied to the primary. The switching IC switches the controller, and that DC is converted into the pulses. So that pulses are fed into the primary, and while the switching period is off here, the remaining energy stored in the primary of the transformer is fed back through this normal UF diode. It is a very fast recovery diode, UF4007, and a TVS diode. A TVS diode is very well known for high reverse voltage and efficient power dropage. So it drops that remaining amount of energy. So a TVS diode and a fast recovery diode is used as a snubber circuit. You may very well know in DC-DC converter, this is a type of a snubber circuit. So here is the thing. So the pulse DC is applied here, and a pulse DC is received at this secondary. So this is the secondary. The secondary uses a diode for rectification of that pulse into almost a continuous DC, and a capacitor is also placed. And this is the auxiliary of the pulse transformer. The auxiliary is used for powering up the isolation barrier. So what this transformer uses is that it uses a feedback from the output of the SMPS to maintain the output. Okay, so there may come some time that the current consumption is high and the the voltage may drop. So to nullify that, it uses a feedback. So what it uses is that it uses a Zener diode, and when the amount of and when it is reverse biased, current flows through it, and it signates, and the signal is passed on from this opto isolator to the control pin of the switching IC. And at that moment, the switching IC, and depending on that action, that whether the voltage is dropped off or the voltage is risen up, the controlling ICs controls its switching actions based on that. So this is how the auxiliary powers of the oscillator and the feedback of the SMPS. So this is in general a controlled system. It has very much benefit regarding to the old power supplies we used, and this is generally used in all of the embedded systems we incorporate today. So now we move to the next part, which is the controller. Okay, so the controller is the brain of an embedded system. It consists of many parts. At center is the CPU, which processes each and everything, computations regarding arithmetic and logic operations, and it has a RAM allocated for it to store the volatile variables, and a flash memory to store the code. The memory is also of two types: the ROM and an EEPROM. An EEPROM is a special, you can say it as a locker where a controller stores its some sort of data which it doesn't wants to lose. Okay, so an EEPROM is a locker for controller, and so there's memories. It also has an oscillator. That's the main thing. It has many chips have an oscillator inbuilt. It may uses an RC oscillator or a quartz oscillator. Many systems have inbuilt. Sometimes you also have to connect it externally, and it ranges from 0 to 40 megahertz depending on the speed of the controller or the application of the controller, which type of controller it is. And it also incorporates ADC, analog to digital converter. It has different resolution like 10-bit, 12-bit, 14-bit. Mainly up to 14-bit resolution is obtained in such controllers. If you want even higher resolution, you need to connect an external ADC. For that, they may go to 16 up to 24-bit resolution. Then comes the IO ports, programmable IO ports. So these ports are the thing where the sensors give their output to, and where the actuators receive their input from. Okay, so these are the hands of the controller, and hands of an, or you may say hands of an embedded system. Okay, now there is PWM to control the somewhat control the voltage and analog to get an analog voltage, and especially the communication. UART, USART. There are many other communication like R2C and SPI. We will discuss them in detail in the later part. Okay, so depending on application, a microcontroller or a microprocessor is used for controlling a process. It is important to list the required number of IOs, analog input and resolution, PWM outputs, and communication needed before selecting a controller for the process. Okay, so what type of controller you choose depends on the process you want to control. Okay, so if a process is like, so if you want to just control and blinking of LED, you won't have to select a very high range controller. Any medium range or small range controller is quite well enough for that. Okay, and so you have to list out such things. Okay, what type of IOs is used, what is the ADC which is required, does it need any PWM output, what type of communication it needs. Okay, there is also a CAN communication, some processes which require. Okay, so you have to select that controller accordingly. Now, controllers are of many kinds. Actually, there are many manufacturers. There are like RAM, ARM, Atmel, ST Microelectronics, Microchip, AVR, Nuvoton, Texas Instruments, which manufactures such controllers. The ARM especially has very high-end application controllers. It's called as the ARM series. The Atmel has medium-range applications. The Atmel and Atene series are very famous of it. The ST Microelectronics has two main series of STM8S and STM32, the 8-bit and 32-bit controllers. They are very widely used. The Microchip manufactures the PIC controllers. They are also very well known. The AVR manufactures the Atmega controllers. Okay, the Arduino, which is well known, uses the Atmega 328P. So that controller is a part of the series manufactured by the AVR. The Nuvoton manufactures many controllers, and 8051 we use today, which we have been using from many time, has been manufactured from Nuvoton, and many other companies are there. Philips also manufactures that. Texas Instruments also manufactures many of the controllers used in the industries. Okay, so these are some well-known companies which manufactures controllers, and its controllers are available, very well known. They are available in low, mid, and high range in 8, 16, and 32-bit operation. So these are the bits operation that a controller does. Okay, they are in low, mid, and high range. And like if you are selecting a controller, what you should mainly do is reading the data sheet which manufacturer provides. Okay, so I will give you a little example how to read a data sheet. So like this is the data sheet of a controller manufactured by ST Microelectronics. It is mainly of STM8S103F3P. And how to read a datasheet mainly depends on what type of applications you need. So first you should know what are the features of it. Okay, so at core it has a 16 megahertz crystal. It is inbuilt, and it is code with a hardware architecture and three-stage pipeline. Hardware architecture, you all know there are two types of architectures: von Neumann and hardware. It uses hardware architecture. It has a three-stage pipeline instruction set. Okay, the memories are, it has the what kind of controller you, what kind of application requires which kind of memory. Means, like if it is a very high end application, it will require a lot of memory, and if it's a low range application, it will require a somewhat medium range memory. So this is what a medium range memory in the controller world looks like. It's almost of 8 KB. Okay, the 8 KB won't sound that enough if you're using Arduino, but if you are very familiar with the controllers, 8 KB is well enough. Okay, so it has 8 KB bytes and 10K data retention cycles. You can flash it for 10K cycles. Okay, 640 bytes of true data EEPROM. That's the locker of the controller, where the controller stores its valuable values which it doesn't want to forget. And the RAM is of 1K byte. You should also look at the clock reset and supply management. It works on 2.95 to 5.5 watt operating voltage. For processors, it's almost from 2.95 to 3.3 volt, but for controllers, it ranges from 2.9 to 5.5. Okay. The flexible clock control, and these are different clock controls available. It uses a 16 megahertz internal oscillator, usually remember 16 megahertz crystal. It also uses an RC internal oscillator, low power crystal. Okay, so clock system and all of that is okay. You should also look at the power management of the IC for applications like the real-time clock or any stopwatch or even a calculator. A very low power consumption is required. It should work for a long time, so you should also look for the power management. Then comes the interrupt management, the most important thing. How many interrupts does it support? The more amount of interrupts you support, the more it is likely usable. The interrupts varies a lot. And the timers, what type of timers are available? 16-bit, 8-bit, 8-bit basic timers with how much prescalers are available for that. Capcom capture channels and all. The communication, which it interfaces, is UART communication, SPI and I2C. All those differ. We will discuss this in the communication slide in the later part. The ADC, it is a 10-bit LSB ADC with up to 5 multiplex channels. So it has got 5 ADC channels. Okay, so you can connect 5 analog inputs to the controller. The IOs, it has up to 28 IOs, input outputs, at a 32-pin package, including 21 high sync outputs. The high sync outputs demands that you don't need to use any external transistor to supply some high amount of current. The controller is able enough to supply that current. Okay, and the robust RSN design. Okay, so this is how in general a datasheet is read. Actually, it is discussed in detail in many more later parts, but this is what a datasheet in general looks like. So you should be familiar with reading a datasheet and deciding which controller is to be used for which applications. Okay, in an embedded system, if you are assigned as a design engineer, like passing from anywhere, so first thing you should basically know is that reading a datasheet of a controller. Okay, so this is the main part. Moving back to presentation, we come up to the integrated development environment. There is the IDE. Okay, so IDE is a software required to develop the code to be loaded into the controller with the help of a bootloader. So these all are the forms of an IDE. So IDE is a software in which the code is written, and bootloader is the one which loads that code into the controller. Okay, each controller manufacturer has its own IDE to code the controller. These all are available. The AVR Studio 4 is available for the ATmega and ATmel controllers. You can code them with it. And the MPLabs X IDE is used to code the PIC controllers, the PIC series of controllers. The Kale Microvision is very well known to support almost all type of controllers. They support almost all. And the IAR also supports almost all of the controllers. And the Arduino is well known. It's an open source platform, and it tries to support almost all controllers, but has its own different embedded C language to do it. Okay. So the main difference between the Arduino and all these things, that firstly is Arduino is an open source platform. Well, these all are the privately owned, so you have to purchase them all. Okay, but the students version of some might be free. Secondly, the Arduino uses embedded C. It is not pure C. It has a dedicated library available to each and every function that it uses. But you have to code in pure C in all of these platforms. You can assign a header file. You can make those header file and assign them by yourself, but no special libraries are available. You have to code in pure C. Okay. Uh, okay. So here is it. So generally, the microcontroller is coded in C and assembly. I'm talking about the microcontrollers. Okay. So C and assembly are generally used. Some IDEs do support C++, C++. Some controllers are also coded with C++. Moving to processors, like processors on the other way can be coded in Python, C, and assembly. Okay, the processors mainly here I'm talking about is the Raspberry Pi, which is very well known. It can be coded with Python. It can also be coded in Python. C and assembly is also supported. Even I've seen Arduino support the libraries for Raspberry Pi. Okay, you can also code with it. Arduino is a very well known. All IDEs are equipped with a text editor, a debugger, workspace, libraries, etc. It is the main console of each and every IDE. You may also be familiar with the Arduino. Now, the main advantage of using this type of IDEs in respect to Arduino is that it may be difficult to use a pure C. Okay, if you're a beginner, you might use Arduino and you may find it easy and compatible more. But eventually, when you will move on to another controllers, when you will be assigned as a design engineer, you will be used to you have to use this type of IDEs. Okay, the main advantage of using these IDEs is that it uses pure C. Okay, if a blink program in Arduino is used in it, it just blinks an LED. Okay, the storage space of that program might be a KB enough. Okay, out of 32 KB, it uses almost 1 KB, almost 1 KB. But if the same program is written in pure C in any of this IDE, it won't take more than 200 bytes of it. Okay, so the program size reduces to almost 1/5 of the program size required in Arduino. And that's the main advantage of it. When the controllers are used in industries, there are thousands and thousands of lines of code. Okay, so you can't use Arduino because the Arduino in backend uses special libraries to support each and every function it provides. Whereas here you will use pure C commands to do each and every task. Okay, here you will have to address each and every register. You have to configure each and every timer. You have to latch each and every port pin you use. You have to configure each and every pin you as input or output, and there are special registers for it. Okay, so that's a work in detail, but at the end, these IDEs are more efficient and than Arduino. Arduino is much more easy to use if you're a beginner, but eventually you will have to use this type of IDEs if you're a design engineer. So it will be good if you get familiar to this type of IDEs earlier. So this is the basic peripheral, interface of any of the IDEs mentioned. It is of the IAR embedded workbench. So it has a text editor. It has a build log. There is also a debug log, which is the build log provides the information of the amount of space which is the program requires, the program occupies. The debug log, while debug log, you can also debug the errors in it. Debug log shows the errors in it. So that's the build and debug log. So, and here is the workspace. The workspace displays the current projects you're working on and the libraries associated with it. And here are the run, build, and compile options for compiling the code, file, and all. So this is what a general interface of any IDE looks like. Okay, so this is the IDE. This is a bootloader. This is what a bootloader looks like. This is the bootloader for the STM controllers. Okay, this is an STM controller. STM it has 103F3P6. STM it has 103F3P6. Okay, so the board is available. It is also compatible with Arduino, but I would recommend to code it with such type of IDEs, because it's, if you even if you are a hobbyist, then you should try this one. Okay, so the IDE gives the codes to the gives the code to the bootloader, first of all compiles it and gives the code to the bootloader, and the bootloader codes the controller. This is how the IDE works. Okay, this is how the controller is coded. So the next part is the sensors. Okay, the sensors form an integral part of embedded systems, as they are the ones through which the controller interacts with the environment. Okay, and sensors are of many types. They are, you can see that sensor applications of smarter world. Okay, like 12% of them are chemical type of gas, magnetic sensors, ultrasound, radio. There are many types of sensors. Okay, depending on the output provided to the controller, they are configured as digital and analog sensors. Okay, the sensor may input any quantity. Okay, the quantity may be physical, mechanical, touch, pressure, anything, chemical, gas, anything. But the output of the sensor will always be in electrical, and it might be in digital or analog form. Digital form will be in the form of pulses. It may be in the form of a communication. Okay, it might be also 0 to 5 volt. Okay, and in analog it might range to analog in 0 to 5. So there are two types of outputs, sensor outputs. Generally, the embedded system employed in food processing, IoT, or mechanical assembly lines incorporates most of the sensors available in the market. Okay, so moving on to sensors, these are the different types of sensors. Okay, so the first is the thermistor. It is the temperature sensor. Then there is an IR sensor. The thermistor is mainly used for temperature sensing, but it's for low end range. If you go for a high end range from 0 to 150 degrees Celsius, you will have to use an RTD for that. So that's a resistant temperature detector. Okay, so that's a thermistor. Then there is an IR sensor of a transmittive type, and there is an IR sensor of receiver type. There are both different things. They are all compatible. These all are shown compatible to Arduino. Okay, this is an IR sensor. Ultrasonic sensor may have used, everyone may have used it. Ultrasonic sensor. It has a pulse output through which the controller knows the distance or anything associated with how much far away the object is from. The gyroscope sensor to detect the tilt or the position of any object with respect to the ground. Okay, the gyroscope are used for that. The accelerometer you may also use. A rain sensor to detect the rain. Soil moisture sensor, they are mainly used in the plant watering systems. A soil moisture sensor. A photo sensor, a photo transistor, a light sensor. It is a type of transistor only, but it is in place of base, you are giving light at its base to conduct from emitter to collector. Okay, a water flow sensor. In this, mainly small motor is kept or a generator is kept through, and when the water flows from here to here, the generator moves and voltage is developed across it, and that's how the sensor gives signal to the controller. A heartbeat sensor. It is very well used in this is not a exact form, but it is very well used in the smartwatches nowadays. The heartbeat sensor. The alcohol sensor you may have used. A color sensor. It uses a chip used for color sensor. In it there is a chip. A PIR sensor. A PIR sensor has an infrared chip placed inside this bulb. Okay, it detects the heat of the moving object, and whenever it detects something move very quickly, it triggers the output. Okay, the sensitivity of this can be changed with these two knobs. Then there's a gas sensor. Okay, it detects the gas, presence of gas. Smoke sensor, LM35. This is also a temperature sensor, LM35. IR receiver. LDR you might have used most of the times as in the solar trekking projects or street light lamps and everything, controlling the street lights and everything. A humidity sensor. These are mainly used in IoT modules to know the humidity and everything. So they transferred through Wi-Fi using the controller. a flex sensor, a touch capacitive touch sensor. It uses whenever you place your finger in it, it will detect it and it will send a signal. A solar light sensor. A solar cell can also be used as a sensor. Okay, the solar cell only, but it's a very small unit of it, and it can be used as a sensor. Like if you want to detect any light. Okay. Also, if you want to check the luminosity of any light, how much, I mean, how many luminous a light is, you can check with this. Then there's a metal detector you may have used, a real-time clock sensor. I don't term it as a sensor, it's a real-time clock. Okay. A vibration sensor, uh, very well used. So these are the sensors which are used at a low level. Okay. But in industry, mainly talking about the electrical industry, the sensors which are mainly used is the RTD. It is placed in the transformer, in the oil pocket, and the temperature of the oil is measured through this RTD, resistance temperature detector. It can detect temperature from 0 to 150 degrees Celsius. Okay, at a normal date, I mean, at 0 degrees Celsius, uh, no, from at 0 to 150 degrees Celsius can measure. Then there is a oil level detector. It measures the level of oil. It is also placed in the oil pockets, and it is placed at the oil pocket sensor and measures the level of oil. And most important is the glucose relay. You might have known, but it is not a dedicated sensor, but it acts like a sensor. It mainly detects the gas which is produced in the transformer when a short circuit or a winding temperament is happening. Okay. A short circuit produces a gas in the transformer tank, which is then passed on through this glucose relay, and it detects it and alarms uh, and triggers the alarm circuit and trips it. It also gives the signal to the SCADA systems for that. So it does act like a sensor. Okay. So these are what sensors in general looks like. We move on to the next part, which is the actuators. Actuators are termed as the hands of an embedded system. Talking about electrical systems, the actuator does the work of making and breaking the circuit, short circuit and overvoltage protection, and voltage and current control ADC. Okay. So the actuators are the one which receives the input from the output of the controllers. Okay. The controllers directly connected it. The actuators receive a direct command from the controller in the form of an electrical control signal. Okay. So what are these actuators, which we will discuss in detail in the next slide. Then the other part is the display. Okay. The display works as an intermediary medium between the user and the controller, whether it's showing any result of a calculation or to show live parameters of a process. Display in general uses most of the output pins of a controller in an embedded system. So display are used very widely. They cover almost 30 to 40% of embedded systems. Okay, they are very widely used as displays. Okay, so it's an intermediary medium between user and a controller, and it shows the result of a calculation, or it may just be used as to display of something like a welcome sign or a scrolling display. You may say whatever, but it is used mainly for that displaying something. Okay, uh, and it also uses most of the pins of a controller. It is somewhat a medium, more top at the top of a medium range application, the display. And if you go for the displays in mobile and LCDs, they are very high range applications. Okay. Also, when the system is complex, display uses most of the processing and memory of the controller. Okay. So these are actuators, and these are the types of displays. So the actuators can be of relay. As you have very known with the relay. The electrical engineers know this relay very well. This is the aspirity relay, which 5 volt or 12 volt available in the range. So this is a relay. This is a contactor. Okay, it's a three phase 4-wire contactor. Okay, so the main difference, many people get confused between a relay and a contactor, is that the contactor connects all of the 3 phases simultaneously. Okay, whereas the relay just makes or breaks just a single phase of a circuit. Okay, so the relay is mainly placed between the live wire and in between the load. Okay, so it makes and breaks the live, whereas the contactor makes and breaks each and every phase of a three-phase circuit. Okay, so that's the main difference. Then the contactor is mainly used to make a circuit and break a circuit, whereas the relays are used mainly in the short circuit protection. Okay, so here we may at the low power applications you may use to make or break, but when we go in industries, there are specific relays assigned to it, like the current overcurrent protection relay or voltage protection relay, short circuit protection relay. Okay, there are many types of relays associated with it. So that's the basic difference between a contactor and a relay. Next, we get the IGBTs. The IGBTs, this is a high power IGBT. The I can give the name, but it has mainly three terminals. Okay, this is an IGBT is used for high power applications. This is a MOSFET. The MOSFET is also used. It's also a type of actuator. It is a gate, drain, and source. Three pins are available. Same is for the IGBT. They both are almost same, but the MOSFET is mainly used in the SMPSs, switch mode power supplies, and the IGBTs are mainly used for controlling, like in drives. Okay, in high power motor drives, the IGBTs are used in place of MOSFETs. The main difference between these two is that MOSFETs are used for very high switching and low power applications, whereas IGBTs are used for high power application and medium range switching. Okay, so that's the part of actuators. Coming to the displays, we get an LCD. It is well known. You may have known. You may have even used it. An LCD. First type of display is the LCD. The second type of display is the OLED display that uses the I2C communication to connect with the controller, to communicate with the controller. We will discuss in the communication section. Some LCDs also uses I2C. Okay, I2C is applicable on both of this. Then there is the 7-segment display. You may have known it very well. The 7-segment display uses 7 pins of an Arduino or a controller, and and the remaining pins depends on the amount of digits you want to control. Okay, but it mainly uses 7 pins and a dot if you want to use. So that's a 7-segment display. Or there is a dot matrix display. It's a dot matrix display. It uses there are thousands of LEDs which are connected, and each and every of those LEDs is lit by a particular pin. Okay, so to lit each and every of these LED, not a 1,000-pin controller is required. In fact, here whenever you see a scrolling display, it mainly incorporates shift registers. Okay, so each and every pin of each and every LED is connected to a pin of the shift register dedicated to each and every section of the dot matrix display, and the controller gives the data to the shift registers. The shift register which is mainly used here is the SN74HC595. It's an 8-bit serial in parallel out shift register. So an 8-bit data comes to in, it controls 8 LEDs. For another 8 LEDs, another shift register is applied. For another 8 LEDs, another shift register, and that's how the array continues. And all of those shift register uses just 3 lines to get the data from the controller. So even a small controller can control the display of such bit. Okay, it just uses 3 pins, and all of the remaining work is done by the shift registers. It keeps shifting the display, and that's how we see a scrolling pattern. So that's the working of the dot matrix display. The 7-segment displays are mainly used in the voltmeter. I mean to say, if you see an electrical panel, you will see many different displays as indicating the the voltage between the two phases, the main voltage, and every other thing, the frequencies, whatever you say. If you go in the other switching sections, you may see a tap position indicator displayed by the 7-segment. Okay, an AVR, automatic voltage relay, voltage control relay, then an OTI displaying temperature. Okay, many things. The LCD is mainly used in the relays. Okay, it is used to assign the numerical relays, I mean to say. The numerical relays, it is mainly uses an LCD to control the numerical relays, which configuration is used to set what the range it should be, how much should be the switching time and everything, how much times it should switch. Everything is controlled by an LCD. The OLED is also used for the same. Okay, so that's the basic use of actuators and displays. And now the last part, which is the communication. Okay, so the communication here referred to is of two types. First is the in-system communication, and second is the system-to-system communication. So when a controller communicates with a certain subsystem inside the embedded system, it is called an in-system communication. Okay, the example of it are between the communication between a controller and external ADC. Okay, it mainly uses an I2C. Sometimes even an SPI is used. The external ADC, I have said it might be used for a higher resolution for 24-bit or 16 or 24-bit resolution. So it communicates to the controller with the help of SPI or ADC, SPI and I2C. EEPROM, external EEPROMs. So in some processes, it might require to store a large amount of data, and at their EEPROMs are used. EEPROMs uses SPI. For that, SPI is quite fast compared to I2C. External flash is also used in some cases to store a certain amount of code externally. So flash also uses SPI communication to communicate with the controller. Then there is DAC, or the digital to analog converter. It uses I2C. It uses because the PWM sometimes is not enough to get the required amount of resolution in the analog voltage. So for that precision, a DAC is used externally. It is available in the many ranges of 12 bit to 16 bit. The DAC is available, and it uses the I2C communication for that. And the in-system communication generally are of I2C. SPI, UART or USART is also a type of in-system communication. UART, universal asynchronous receiver transmitter, and universal synchronous asynchronous receiver transmitter here are used. So this is the in-system communication. Now, when a controller communicates with another controller of an embedded system, which are interconnected for data sharing, having their own individual processes to do, is called a system-to-system communication. Okay, so when we talk about two embedded systems communicating with each other, we are talking about the system-to-system communication. Okay, so like in say like your laptop incorporates almost 7 to 8 types of different embedded systems dedicated to do each and every different work, and there is a processor which governs all of them. Okay, so when such type of systems communicate with each other, that type of communication is also called as the system to system communication, because they are in own as an embedded, they work as their own as an embedded system, and they work together by sharing the data with each other. Okay, so that's in system to system communication. These communications can be long range too. Okay, this communication doesn't really necessarily means that it is inside a small space. Okay, it can range from many meters. Okay, it is long range. It can be a long range communication, even kilometers. In the electrical systems, CAN, Bluetooth, Wi-Fi, RS485, USB, a 4 to 20 milliampere current loop, HART, and Ethernet are the examples of such type of communications. Okay, so we'll look at some examples of it. So this is the example of an I2C communication. There are two different there are two ICs, masters and slave. There is mainly this is a controller, and this is an external ADC or flash device or EEPROM, many associated to it. DAC mainly. So there are it's a two-wire communication. The first is the SDA, through which the data is exchanged, and the second is the clock. The master gives the clock to the slave, and the slave gives the data accordingly to the clock, latches the data according to the clock, and that's how the communication is done. So that's the I2C. Another thing to mention that it can be done between many devices. Each and every device will have their own unique ID through which the master will communicate with slave. Okay, so that's I2C. Now moving to SPI, the SPI can mainly is used between the communication between EEPROM and flash. Okay, it's quite fast compared to the I2C. Okay, so the communication between uses 4 pins actually. The first pin is the master out slave input, which is connected to the that same pin on the another slave device. The second is the master input slave output connected on the second same device, which is the slave is given here. The data is given from master to slave, and on this pin the data is given from slave to master. Okay, master receives the data from here and gives the data from here. Then there is a clock pin. The master clocks the slave. Okay, and then there is a separate pin allocated for selecting number of slaves. Okay, in SPI you can also include many of the slave devices with each other. Many of them can be included, and a dedicated pin is given to each of them. Through this pin, a dedicated unique ID is pulsed, and the slave which has that unique ID responds to that unique pulse. Okay, so that's the SPI, and it's quite fast compared to I2C. Then there is UART. UART uses 3 pins. The first is the RX, is the receiver pin. The second is the TX, that is the transmitter pin. And third is the ground one. It is in UART communication, it is necessary to have both the systems grounded together. So the ground pin is connected to ground of the other system. So the RX pin is connected to the TX of other, and the same is vice versa. So here the data is transferred from RX to TX and is received from here. So mainly if you consider it as a controller and any other device, that's how the communication occurs between the two in the UART type of communication. So that's a part of these three are the in-system communication. These all are the part of the system-to-system communication. So the first is very well known. It is you might have seen is the Bluetooth communication. The Bluetooth communication itself, the module itself uses UART to communicate with the controller, but it transfers the data. It transfers the data through this antenna, through radio signals. Okay, so that's the Bluetooth. The second one is the Wi-Fi. Okay, you might have known this chip for IoT projects and many more. It is mainly used. Its name is ESP8266. It's a microcontroller with a Wi-Fi capability enabled. Okay, so you don't need a special controller for enabling the Wi-Fi module. You get a controller and both a Wi-Fi module in a single same chip, and it is very widely used. Okay, so this is the Wi-Fi module. Next is the USB. Okay, so you're very familiar with this sign, that is a USB. The USB communication is also very fast. It is very fast in compared to all of this. Okay, so there's a USB and there is a chip, that is a CS340G. It's a USB to UART converter chip. So mainly a converter is connected, a controller is connected here through UART, and any dedicated system like a computer is connected here and a UART is connected here. When a bootloader loads the code into the controller, it mainly uses this type of communication, USB communication. Okay, so here is the main chip which does all of the work for that. Here is the USB, here is the UART output. And this is the chip CS340G. The next one, this is the RS485. Okay, the RS485 communication is very widely used in the PLCs. Okay, the PLCs used to communicate with other different PLCs or other different subprocesses with RS485 communication. RS485 is quite similar to USB communication, or you may say it is also quite similar to the UART. This chip, the chip itself shown here is convert the RS485 communication to the UART communication. Okay, so this is the chip for that. The transmitter, this particular thing is called as the 4 to 20 milliampere current loop transmission. Okay, this is the most widely used and well incorporated system used for communication by PLCs and every other thing. It is used very much industrially. Okay, so this is the 4 to 20 milliampere current loop. We'll discuss this in the next slide. And here is the Ethernet. You have all known it very well. Okay, so these are the type of communications an embedded system uses. Now, the most important aspect of communication which industries uses right now is the 4 to 20 milliampere current loop. Okay, so a current, no matter how long is the distance, the current never changes. Okay, if there is a two-wire system, if you transfer a voltage across it, that then after due to resistance and IR drop, the voltage might get different at the other part of at the end of the wire. But if there is current, you will and if you apply a constant current source at one end of the two wires or a circuit, you will always receive the same current at the other end. So the current is mainly used to send the amount of values or the result to a different system. Okay, so here is the 1 to 5 volt signal range, or here it is this signal which is used to send. It can be anything. It might be like a temperature, which is it might be an output from the RTD. Okay, from 0 to 150 degrees Celsius, which is ranged from 0 to 1 to 5 degree in the form of 1 to 5 degree, and it is given to this op amp. Okay, so this op amp acts in the inverted configuration. It has got a feedback. Okay, so the voltage at here, the non-inverting terminal, will be equal to the voltage at the no matter what anything happens, the voltage at both the non-inverting and inverting terminals of the op amp will be equal. So in order to get the same voltage at the inverting terminal as of the non-inverting terminal, the op amp pumps that much amount of current through which the potential divider formed between these two gives the voltage that is equal to the non-inverting terminal. Okay, and that so here the load which is shown is actually the load which is connected in the different system. Okay, so the positive and negative of different system is connected here, and one system is connected here. So a system measures the value, it gives it to the buffer, it gives it to the non-inverting terminal, and these two systems are differently connected to each other, the two-wire system, and a current is pumped through it. Okay, so that system, this resistor R load is mainly of 250 ohms. Okay, so depending on whatever the value or in the range of 1 to 5 volt is, the current in the form of 4 to 20 milliampere will be produced, and that current will flow through it, and across this there will be an IR drop. Okay, and a proportionate voltage such as this voltage will be produced across this load, and that's how the another system will know what is the value measured here. So that's the 4 to 20 milliampere basic of how this 4 to 20 milliampere current loop works. Okay, so this is how we reach at the end of the webinar, and I think the main objective of getting you thorough with the embedded systems is, I somewhat say, is completed. If you have any questions, you can ask to me. So, hello, Chirag sir. Hello.
Yes, sir.
Are there any comments or any questions they want to ask?
No, sir. Thank you, sir. So thank you for
Okay.
sharing your valuable time and being with us. So this might be helping our student for their future projects, sir. Thanks a lot,
Sure.
sir.
Sure.
Okay.
Sure.
Thank you.
Okay.